Hey, every now and then, after you've done all the other asymptote stuff, sometimes it's just easier to look at end behavior in general of a function. And the end behavior of a function usually tends toward a specific asymptote, and sometimes on a slanted asymptote or what's called an end behavior asymptote. And those work for large values. And what we can do is take a very complicated, long drawn out polynomial, and we can just look at end behavior, because a lot of times with asymptotes and large values of infinity or whatever, we just need to know what's going on in the extreme locations, way big numbers or way small numbers. And so what we're going to do is look at a problem here and use an end behavior model to try and figure out, maybe what the limit is, or what's it going to, or can I show that these two things are the same for large numbers? So that's what we're going to do here. And I'll sum it up again. We can sometimes model the behavior of a complicated function by a simpler one that acts virtually the same way. Again, we're not interested in numbers that are small, close to zero. Okay, end behavior means large numbers. So we want to show that f and g are different values, are different for small values of x, but are similar for very large values. So let's look at our hint, which says that we should put f over g and look at a limit. So when I do that, I get this. And we're going to use some rules of fractions here that I hope you can remember. And if you can't, maybe after working this problem, will have jogged your memory. We did work a very uncomplicated, similar question earlier. But remember, we can separate everything onto the top over the bottom. So I would have 3x to the fourth over 3x to the fourth minus 2x cubed over 3x to the fourth plus 3x squared over 3x to the fourth minus 5x over 3x to the fourth plus 6 over 3x to the fourth. And so when we're working these problems out, we're trying to find these limits. Notice that a lot of these limits will reduce a little bit. For example, the first guy right here reduces all the way down to 1. The next guy, minus, reduces to 2x, 2 over x. The next guy reduces to 1 over x squared. The next guy reduces to 5 over 3x cubed. And the last guy reduces to 2 over x to the fourth. Okay? So then when we look at these things, what ends up happening is all of these values, they all tend towards 0, because the top now never changes and the bottom is growing larger. So anytime that happens, you're going to have a 0 for your limit. So if we put our limit question back on this guy as x approaches infinity, all of these go to 0. And that leaves me then with a 1. And so I've got this true statement right here. And so what that tells me then is that for very large values, not close to 0, but large values like millions, these two different functions are virtually the same.